Okay, in this video, I want to review the concepts of gravitation and circular motion as a review for the test. We're going to start off with the two primary equations for the unit. One of them is an equation for calculating the force of gravity between two objects. So that is Fg, force of gravity, that's a lower or subscript g, equals capital G, the universal gravitational constant. This is just a number. It's 6.674 times 10 to the negative 11 Newton times meter squared over kilogram squared. The units are weird, but it's a number. Okay? That gets multiplied by the mass of the first object and also the mass of the second object, and I use a capital M and a lowercase m to differentiate between the two objects. If we had two different masses, we'll typically put the bigger one in for capital M and the smaller one in for lowercase m, although it usually doesn't really matter. Once you multiply those three things together, you need to divide by the distance between those two masses as measured from their centers, that is center to center, and square that distance. So this is the force of gravity equation given to us by Isaac Newton. The other main equation for this unit is an equation for the centripetal force acting on anything that moves along a circular path. That is, this is a force that is centripetal in nature. Centripetal means towards the center. You can also just think of it as force towards the center. Okay, anything that's moving along a circular path feels some force towards the center, and this is how you calculate it. It's the mass of the object that's going around times its speed squared divided by the distance, where this distance is the radius of the circle. Okay. These are our two main equations. We know from Newton's second law that force equals mass times acceleration. A force causes a mass to accelerate. This applies here as well. This force of gravity causes one of these masses to accelerate. If we line these equations up, we say, okay, here's my F, that corresponds to this F. Here's my M, that corresponds to this M. So this must correspond to an acceleration. And this is the expression you would use to calculate how fast something is accelerating when gravity is pulling on it, if gravity is the only thing pulling on it. So this is an acceleration. Now, because this acceleration is caused by gravity, a lot of people don't call it A, they call it G, or lowercase g. That's confusing to a lot of people though. And a lot of people see this and say, this is gravity, when they really should be saying, this is an acceleration caused by gravity. The G is a reference to what causes the acceleration. We come over here. Here's the force, here's the mass, this must be the acceleration. This is the force towards the center of a circle that allows some mass to move in a circular path. This right here is how you would calculate the acceleration of that object moving along its circular path. And because this is for an object moving along a circular path, a lot of times people will put a C as a subscript on the A and say this is the centripetal acceleration. This acceleration is directed towards the center, just as the force is directed towards the center. Okay, now we actually move on to solving a problem. So, here's a problem we're going to tackle. Find the gravitational force between the Earth, and here's its mass, and an astronaut, and here's her mass, when the astronaut is 7 million meters from the Earth's center. One of the first things you're going to have to do when you tackle any of the problems in this video or on a test is identify what equation to use. What are we actually looking for here? And the answer is we're looking for a force. We have two equations for force. We can use Fg or Fc. Which one is appropriate? So we say, okay, am I finding force of gravity or the force towards the center of a circular path? It turns out it's both. Because if we have a planet here and a little astronaut here, this astronaut is being pulled towards the planet, okay? And that astronaut, let's say, is orbiting, moving along a circular path. That astronaut's going to feel a force towards the center of the circle, and that force will be gravity. So actually, both of these equations are valid equations, and we could use either one of them, but only one of us is going to allow us to calculate the gravitational force. I take that back. Actually, both of them would allow us to calculate the gravitational force, because force is force, and this is the only force, and if we calculate that force, we'll have our answer. However, only one of these two equations we have the right stuff to plug in. Let's put it that way. I want to calculate a force. Both of these equations apply, because the force is gravity and the force is towards the center. If I look at this equation over here, I'm stuck, because I don't know what V is, so I can't plug in for V, so I'm stuck. So I come over here, I actually know what to plug in on this side, so this must be the equation to use. So the force of gravity is the constant G, 6.674 E negative 11, times the mass of one of the two objects. Typically we put the bigger mass here for capital M, 5.972 E24 kilograms, times the mass of the second object, 75 kilograms, divided by the distance between them squared, measured from the center of the Earth to the center of the astronaut, which is this number, squared. Okay? When you multiply these three things together and divide by this squared, you get 610 newtons. Moving on. At what rate is the astronaut accelerating or falling towards the Earth? Everything in orbit around the Earth is accelerating towards the Earth. In other words, falling towards the Earth. When you read this word accelerating should tell you that we're looking for A, not F, but A. Okay? Is this acceleration due to gravity? And the answer is yes. Therefore, we are allowed to use this equation right here. Is the acceleration towards the center of a circle? And the answer is yes. Therefore, we're also allowed to use this equation. We could use either equation. So which one do you pick? Pick the one where you have the right stuff to plug in. We don't know the speed, v, so we're not going to use this equation. But we do know this stuff. So we're going to use this equation. So g, remember how sometimes people use g instead of a? This is the acceleration caused by gravity. It is an acceleration, it's not a force. It's equal to g times m over d squared that is 6.674 e negative 11. I don't ever put the units here because they're messy. There should be units. Here's the mass of the Earth. I'm not going to put the mass of the person, only the mass of the Earth. The mass of the person is irrelevant. Just like on Earth, it doesn't matter how much your book weighs when you drop it, it's going to fall at 9.8 meters per second squared. The distance is that same 7.0 e6 meters squared. And what do we get? We get 8.13 meters per second squared, which is only a little bit less than 9.8, which is what we find on the surface of the Earth. Oh, you can't see. I'm sorry. Here we go. I'm pointing right here. Okay, so again, this is how you calculate the acceleration of gravity. Not gravity, but the acceleration caused by gravity. And here's the value. Okay, moving on. Problem 3. To avoid falling into the Earth, the astronaut must have a large sideways speed or orbital speed. Find it. Okay, so if we look at this picture, if this astronaut is being pulled inwards towards the ground, why doesn't she actually fall into the Earth and crash? And the answer is because she's also moving towards the side. Okay, and she starts to move a bit out, and gravity pulls her back in. And she continues to move a bit out, and gravity pulls her back in. So really, gravity is only keeping her from moving further away. Without this sideways speed, she would just pull straight down. Okay, so problem number 3. We want to find a speed. That's v. So what equation do we use to find v? We come up to the top and we say, well, this one feels easy because there's no v over here, so it must be this one. The force towards the center of the circle is equal to the mass of the astronaut times her speed squared over d. Well, I keep needing to move the paper around. Sorry if you can't see what I'm saying sometimes. Here we go. Okay. Now, the force towards the center, what is it? It's not stated right here, but we found it earlier. The force towards the center is gravity, and earlier we found that it was 610 newtons. The mass of the astronaut, this is her mass, is 75 kilograms. Her speed squared goes right here, we don't know it, and the distance from the middle of the Earth to the middle of the astronaut is 7.0 e6 meters. So we can solve this for v. We'll multiply both sides by 7 million, and it will cancel out here. Okay, and then we'll divide both sides by 75 kilograms. So again, I multiply both sides by 7 e6, which is 7 million. And then divide both sides by 75 kilograms. Okay, so this times this divided by this equals v squared. Then I want to take the square root. And when I take the square root, I get for speed of 7,545 meters per second. Now, what if you had not already found the 610? Here's what you would do. This is what you can do for any satellite. Satellite is anything orbiting another object, typically a planet or a star. An astronaut is a satellite. The Hubble Space Telescope is a satellite. The moon is a satellite about the Earth. The Earth itself is a satellite about the sun. Okay? So here's what you would do. You would say, this is my equation. The force towards the center is mv squared over d. What if you don't already know Fc? You know that it's gravity. The force towards the center is gravity. So you go find your equation for gravity, and you plug it in for Fc, and you say, well, gravity is gmm over d squared. Gravity is gmm over d squared. And that is equal to mv squared over d. Okay? And so now I have an expression that allows me still to calculate this v. Okay? You basically just want to simplify this and calculate v. Notice that the little m, the 75 kilograms, the mass of the astronaut, does cancel out. So I didn't even have to tell you what her mass was for you to solve this particular problem. It does not matter. I'm going to multiply both sides by d, and I get gm over d equals v squared. Take the square root, and I get v. So this is another way to find the speed of a satellite. Not the speed of a car or the speed of an earthworm, but the speed of a satellite. So gm over d. Okay, and this is the mass of the Earth. And this is the distance. It's not diameter. It's distance from the middle of the Earth to the astronaut. Okay, another name for this is radius. This is the radius of the circular path that the astronaut is taking. This right here would get you the exact same answer. Okay, as what we got earlier. 7545 meters per second. Okay. Moving on. A race car is driving along a circular track at a constant 67 meters per second. What friction force is necessary to allow the car to maintain this speed along a curve of radius 200 meters? And we look at our equations, and we say, what are we trying to find? What force? I'm looking for a force. I have two force equations. Which one do I use, or am I allowed to use either one? And we say, look, we can't use this force equation because it's not gravity that's pulling on the car. It's friction. I mean, gravity does pull on the car, but that's not what we're talking about. We're trying to find the friction force. The friction force. Sorry, here we go. The friction force. So we're not going to use the gravity equation to find the friction force. But because this friction is pulling towards the center of the circle, we are allowed to use this equation, the force towards the center. Force towards the center is mv squared over d. This is not a gravity problem. This is a centripetal force problem. Okay? What friction force is necessary to allow the car to maintain the speed of 67 at a radius of 200 meters? Okay? Well, it's going to equal the mass of the car. We weren't given that, were we? So here's the thing. we should have been given the mass of the car. We can pretend like it's 1,000 kilograms. Let's do that. So this is 1,000 kilograms. Times the speed squared, 67 meters per second. Square that. Divide it by the distance from the middle of the track to where the car is. That distance is also known as the radius of the circle. And that distance is 200 meters. 1,000 times 67 squared divided by 200. 1,000 times 67 squared divided by 200 is 22,445 newtons. So that is the force towards the center, and more specifically, that is friction. This is just a generic expression that means force towards center. This is what the actual force is. The force is actually friction. Friction is the force that points towards the center. This is how you really should label it, because this is more specific. Okay, on a free body diagram, you would label your vector, your force vector, friction, and you would say it has a value of 22,445 newtons. Okay. Here's another problem. Find the gravitational force between a tree in Austin and a tree in Boston. Force. We have two force equations. Is this the force towards the center of a circle? No, certainly not. These trees aren't moving in a, around and around in, well, don't overanalyze. These trees aren't moving around a racetrack or moving in a circle, at least the same circle. This is a gravitational force, Fg. And Fg, we have that equation. We take our constant, 6.674 e negative 11. We times it by the mass of the first object times the mass of the second. Don't worry about which is bigger. It's both 9,000. Which should I put in which spot? It doesn't matter at all, because 9,000 times 9,000 is the same as 9,000 times 9,000. And then you divide by 2.736 E6 squared, and you get 7.22 E negative 16 newtons. A tiny force. So you have one tree over here and another tree very far away, and those two trees are pulling on each other. This tree pulls this tree towards it, and this tree pulls this tree towards it. And the force on this tree is 7.22 E negative 16 newtons. And the force on this tree is also 7.22 E negative 16 newtons. And if this was the only force on the tree, it would accelerate, albeit slowly. It's not the only force. There's other forces, and they do tend to cancel out, and so this tree does not accelerate. Acceleration is 0, but anyway, the force of gravity here are these two numbers. Okay? Moving on. Find the orbital speed of a 3,000 kilogram satellite orbiting a planet at a distance of 8 million meters from its center. So if it helps, draw a picture. Here's the planet, here's the satellite. The satellite is orbiting here at a distance of 8e6 meters. The mass of the planet is 7e24. The mass of this satellite is 3,000 kilograms. We're finding the orbital speed. Okay, that's v. So if you remember from before, v appeared in the equation Fc equals mv squared over d. V did not appear in the gravity equation, so you're initially directed towards this equation. Okay, here's M, the mass of the satellite. Here's D, the distance from the middle of the planet to the satellite. We can find V as long as we know F, but we don't know F. What that tells you is that you need to realize that the force towards the center is gravity, and go set this equal to the gravity equation like we did before. Gmm over d squared. Okay, this is what you do when this alone won't allow you to find the V. You set this equal to the gravity equation. We're allowed to do that because the force towards the center is the force of gravity, and this is how we find the force of gravity. Okay. So this is what we use. When you clean this up, you get V equals the square root of Gm over d. We got this earlier. That's 6.674 e negative 11 times the mass of the planet is 7e24. The distance is 8e6. You take the square root. Okay. I'm not going to finish solving it because you could do that. Find the speed of a 0.05 kilogram ball tied to a string being swung in a horizontal circle of radius 0.2 meters. The tension of the string is known to be 10 newtons. Let's just see if we can pick out the right equation. Would it be the FG equation? Would it be the FC equation? Okay. Would we use the fact that this right here is equal to little g? Would we use the fact that this right here is equal to AC? What do we use? So what are we looking for? We're finding the speed of a ball that is moving in a circle. So we want this speed right here. Okay. So we're going to use this equation. Is this one of those times where we're going to have to set this equal to gravity? And the answer is no, because gravity is not what's pulling towards the center. It's a string that's pulling towards the center. So you're not allowed to set this equal to gravity. Hopefully this equation works, because you can't set it equal to anything else. This is it. This is our only chance. The force towards the center. Oh good, we're given it. It's 10 newtons. Okay, and the mass is 0.05, and the d is 0.2, and yes, we can solve it. So you can solve it. Yes. Okay. I'm not going to do it. Find the acceleration of gravity on the moon. Okay. So that is, if you are on the moon, here's the moon, and you are an astronaut on the moon. I'm just not drawing a good astronaut today. Okay. Voila, that's the astronaut on the moon. That's horrible. Okay. But anyway, this astronaut drops something like a hammer. How fast does the hammer fall to the ground? That's what we're asking, really. The acceleration caused by gravity. That's what they mean by acceleration of gravity. The acceleration caused by gravity on the moon. So gravity makes things fall how fast on the moon? It's not 9.8. That's Earth. It's going to be slower than that. If you drop something on the moon, how fast does it fall? And by that I mean, at what acceleration does it fall? So, what acceleration are we going to find? This acceleration caused by gravity, or this acceleration in a circle, or towards the center of a circle? Well, this thing is not falling in a circle. It's falling straight down. It's caused by gravity. You're using this one. So G equals Gm over d squared. You need G, you need the mass of the moon, not the hammer, but the moon. You need d, the distance from the middle of the moon up to the ground level, which is also known as just the radius of the moon. Right? The mass of this little hammer doesn't matter. It's not in the equation. Okay, you can do that. The meteor is accelerating towards the Earth at 5.2 meters per second squared. How far away is it? How far? That's d. Okay. We haven't done one like this yet. How far away is it? Well, we have d on both these equations, in both of these equations. Which one do we want to use? Is gravity involved? Is gravity pulling on the object? And the answer is yes. Okay, so maybe it's this one. Is this object moving in a circle? Possibly. If it's orbiting, yes. If it's actually like plummeting into the earth, it's not really circular. So it's not really probably moving in a circle. Okay, so really we should use this side. Plus when you go to plug in numbers, you're going to find out you couldn't have done this one anyway, because you wouldn't know like what to plug in for the V. But on this side, how fast is it? Oh, how far away is it? Okay. Well, we're told that the acceleration is 5.2 meters per second squared. That means little g is 5.2 meters per second squared. And we know little g is equal to big G times m over d squared. And we're just going to, sorry, let me scroll up. Here we go. Little g is equal to 5.2. Little g is defined as big G m over d squared. We know this mass. This is the mass of the Earth. We know this we're going to solve for this d. Okay. So you just say 5.2 there equals g 6.674 e negative 11 times the mass of the Earth, 5.972 e 24. Yeah, I didn't give it to you right there. We looked at it earlier. Over d squared. You can solve that for d. Okay. That's it. Hopefully this video helped.